Yo, extra what? Yeah, it's got pencils. Oh, help yourself. All right, so where are we at? The two spinners at the right are spun. Find each probability. Well, in talking about probability, for instance, you know, probability of one event and then probability of a second event, like spinning this spinner, then spinning this one. Well, what about what's the probability of having a first event and then having a second consecutive event? Well, that probability is you take the first probability or the probability of the first event and multiply it times the probability of the second event. And so I got these two spinners. I'm going to spin the first one. I'm trying to figure out what's the probability of getting a 2. Well, so that's my first event. The probability of getting a 2 is 1 out of 8. I've got 1, 2 that's there, but I've got 8 total options. So that's 1 out of 8. And then what's the probability of getting a B on this spinner? Well, yep. There are 2 B's on here out of 6 possible things that can happen. So that's 2 out of 6. So the thing is when I get right here. So let me say that a different way. Wow. So at this point, what I've been suggesting is that if you can reduce these fractions, that you reduce them. Because one, reducing them right here, you're usually dealing with smaller numbers. You're usually dealing with easier things to reduce. Like this right here, these are both even numbers, so I can just divide by 2, and I get 1 over 3. So when I multiply them, now I've got 1 over 8 times 1 over 3. That's 1 over 24, and that's my probability. Now, if I didn't reduce it, I would have got 2 over 48. And I would have had to reduce it because 2 over 48 is wrong. You always reduce your fractions. Always. 2 over 48 was wrong. 1 over 24 is my answer. So um, it's not this problem isn't really a bad example, but the reducing that you do isn't really that big of a deal right here. But I'm sure there's a different problem that's going to make a little more sense as we keep it moving. So let's see. I got what's the probability of getting an even number on the first spinner and then getting a C on the second? So the first one, let's see, is 2, 4, 6, 8. So there's 4 possibilities out of 8. So that's 4 out of 8. And then we got our second event. There's only one C out of 6 possibilities. So that's 1 out of 6. Well, 4 over 8 can be reduced. There's a number that goes into the top and the bottom. It's just 4. So if I divide by 4, top and bottom, I get 1 over 2. So I've got 1 over 2 times 1 over 6. That equals 1 over 12. And that's my probability. Now, if I didn't do that, I would have got 4 over 48. 4 over 48 is wrong. Now, if you get 4 over 48, which isn't a problem, you just got to remember that you have to reduce till you can't reduce anymore. And so that's that. So question, are these events, are they independent or dependent? Say it again. They're independent because the first spinner doesn't affect what happens on the second spinner. So they're independent. So my next probabilities. The first one, I want to get a number that's less than 7. And then on the second one, I want to get an A. So less than 7, that means it's not 8, it's not 7. So we got 6, 5, 4, 3, 2, 1. So that's 6 possibilities out of 8. So that's for my first thing. I got 6 out of 8. Well, I can reduce that by dividing by 2, top and bottom. So I get 3 over 4 is my probability for the first event. And in the second event, getting an A, well, out of 6 total possibilities, 3 of them are A. So that's 3 out of 6, or 3 over 6. And that can be reduced by dividing the top and bottom by 3, and I get 1/2. So I got 3 over 4 times 1/2. That becomes 3 over 8. That's my probability. Now, if I didn't do that, I would have got, what is that, 18 over 48. Now, 18 over 48 might be a little tougher for some folks trying to figure out what number goes into 18. It also goes into 48. Well, they're both even numbers, so you can divide by 2. But they're also numbers that can be divided by 3. They're also numbers that can be divided by 6. So as long as you keep going, you could start with 2 and then do 3 if you wanted to, as long as you keep going until you can't reduce anymore. But my suggestion is that your division is just easier. Your reducing is easier if you attack it right before you multiply as opposed to after. So, number 4, what's the probability of getting an odd number? It's the same as getting an even because we got 8 possibilities. So the first event is 4 out of 8, which can be reduced to 1/2 by dividing by 4, top and bottom. Then the next one I want to get is not B. So if I look at, I got 6 total possibilities and I want not B. So I don't want this and I don't want that. That means I've got 1, 2, 3, 4 possibilities. So my second is 4 over 6. And 4 over 6 can be reduced. I can divide by 2, top and bottom, and get 2 over 3. So then I just multiply. I got 1/2 times 2 over 3. Well, also right here, once I get to this point, another thing you should do is butterfly or look to cross cancel or look kitty corner to see if you can do any division there, if you can reduce anything there. So in this case, okay, so in this case, I've got a 2 on the top and a 2 on the bottom, even though they're not on the same fraction, they're kitty corner. And so I can divide those two things by 2. So that eliminates them, they become 1. And so now I got 1 over 1 times 1 over 3. So my probability is just 1 over 3. Now, you could have started with 4 over 8 times 4 over 6 and got 16 over 48. And then you could have tried to divide that or reduce that. You could say 2 goes in there. You could say 4 goes in there. You could say 8 goes in there. There's a bunch of numbers that go in there. But you got to keep reducing until you can't reduce anymore. And it breaks down all the way to 1 over 3. Because you can divide the top by 16 and the bottom by 16. 48 is 3 times 16. So you get 1 over 3. And then finally, I've got the probability of getting something greater than 5 and then not getting C. So if I look here, and I'm talking about greater than 5, or greater than 5 is 6, 7, and 8. So my first event is there's 3 possibilities out of 8, and that can be reduced. And then I got my second event. Second event is not C. Well, not C means I'm looking at all of those possibilities. Well, that's 5 out of 6 possibilities. So I got 3 over 8 times 5 over 6. Now, I can kitty corner or cross cancel or butterfly right here. I can divide the top number by 3 and this bottom number by 3. And I get a 2 right here and a 1 right there. So now I got 1 over 8 times 5 over 2. So that becomes 5 over 16. And that's my answer. Okay, what didn't you get? Okay. Well, if I multiply it the way it is, I've got 3 times 5, that's 15. And then I've got 8 times 6, that's 48. So let's just go through the divisibility rules. 2 don't work because 5 is the ending number. That's not even, so 2 don't work. Divisibility rules for 3. You add up your digits. If that number is divisible by 3, then the number that you started with it is divisible by 3. 1 plus 5 is 6. Is 6 divisible by 3? Yep. So then that means 15 is divisible by 3. Um, 4 plus 8 is 12. Is 12 divisible by 3? So 12 is divisible by 3. 48 is divisible by 3. So I divide those both by 3 and I get 5 over 16. So anybody have any other questions about this first section? Anybody have any other questions about this first section? Yes, ma'am. You might guess. Okay. So now we're looking at this next set of events. We're talking about these cards. So there's 10 yellow cards, 6 green cards, 9 orange cards, and 5 red cards. And a stack of cards turned face down. Once a card is selected, it is not replaced. That is important. And then find the probability of each. Well, there's a total of how many cards? There's a total of 30 cards. 16 plus 14, that's 30. Are these, well, let's just try it. Well, let me say it first. Okay. Are these events going to be independent or dependent? Are these going to be independent or dependent? They're going to be dependent because the first event has an effect on the second event. Now, how does that play out? Well, if we take one card away and don't replace it, the total number of cards goes down. So if I started with 39 cards, I pull one out, I don't have 30 cards anymore if I don't put it back. So that affects the next thing that I do. So anyway, so my first event right here, well, first off, just make sure that I got one event and then a second event. So that means I'm going to take the probability of the first event times the probability of the second event, just like we did before. Only this time we're talking about dependent events, not independent events. So a red card, there's 5 of them. It's 5 out of 30. So that's my first event. Well, I can reduce that. So I'm going to divide the top and the bottom by 5 because the divisibility rules say that if your number ends in 5 or 0, you can divide it by 5. So divide both the top and the bottom by 5 when you're reducing. You have to divide by the same number, top and bottom. You can't choose different numbers. So that's 1 over 6. And then I got my second event. My second event is choosing an orange card. Well, there's 9 orange cards in there. So it's going to be 9. But the thing is, there isn't 30 cards anymore because I took one out and it hasn't been replaced. So that's 29 cards. So I've got 1 over 6 times 9 over 29. Now, I can butterfly. 1 and 29, they don't have anything in common but 1. And 1 doesn't change anything. But 6 and 9, they do have something in common. They can both be divided by 3. So that's what I'm going to do next. So I'm going to divide 9 by 3, and I'm going to divide 6 by 3. That gives me a 2. That gives me a 3. So now I'm looking at 1 over 2 times 3 over 29. There's no more reducing to do, so I just got to multiply. 3 times 1 is 3. 2 times 29 is 58. And that's my answer. So next, 2 green cards. So I got my first event. There are 6 green cards. So my first probability is 6 over 30, or 6 out of 30. So I'm going to say it again. Okay, I just didn't hear you. Okay, so I'm going to divide both of those by 6. And so my first event ends up being 1 over 5, or 1 out of 5 as far as my probability goes. Now my second event, I want to pull another green card. So 2 things happen. One, the number of green cards went down because I pulled one out. It's only 5 left. So That's the first thing that I'm going to be looking out of 5. The second thing is because I pulled one card out, it's not 30 cards left. It's 29 left. I can't do any reducing there, so I got 1 over 5 times 5 over 29. And like I told you before, so then we're going to butterfly. Yes, it does. What's wrong? Okay, allow me to say it again. You start with 6 green cards, right? 6 green cards. This is the probability that you get what you want. So um, the probability says because there's 6 green cards out of 30, it's just 6 over 30 is my possible probability, right? And I can reduce that to 1 over 5. So that was the first thing. So remember that this scenario is going without replacement. So if I pull out a card that I want, it doesn't go back. So I pulled out a green card. So that means the number of green cards I had went down. It went down to 5. Also means that my number of cards that were total at 30 went down to 29. So the odds of pulling another green card is 5 out of 29. It's 29 total and 5 green cards left. So I get 1 over 5 times 5 over 29. And so this is when I say about the butterfly or cross cancel. If you're not familiar, I keep saying butterfly because Miss Crow used to teach, or she still does, teaching reducing like or cross canceling like this. She would do those 2 little loops and then say they look like a butterfly. And so that's why I keep saying butterfly. So anyway, the thing is, I got a 5 on top and I got a 5 on the bottom, so I can divide both of those by 5. And they become 1. So now I got 1 over 1 times 1 over 29. And that's just 1 over 29. That's my answer. Now, the reason that we do something like that is because otherwise you might have had 5 over, let's see, what is that, 145? And if you leave it like that, it's wrong. If you're trying to figure out what to reduce, that's a lot more, well, it's not a lot more challenging, but it's more challenging than just saying, oh, there's a 5 up top and a 5 on the bottom. I can divide those 5s out, or I can reduce those 5s out. So I'm trying to convince you that for the most part, it's always going to be easier to do your reducing before you do your multiplication. But it's just a preference. You do you. All right, so the next one. I got a yellow card and then a card that is not orange. So let's look at the first event. So my first event is I want to draw a yellow card. So there's 10 possible yellow cards out of 30 possible cards. So 10 over 30. And say it again, ma'am. That's fine. If you reduce it by 5, you get 2 over 6. The thing is 2 over 6 can be reduced. Now, if you choose not to reduce it, that's fine. The thing is, though, if you don't go to the lowest possible thing, that just means you're going to have to reduce later on. If you do all of your reducing before you multiply, 9 times out of 10, you won't have to do reducing after. So dividing it by 5 is something that you can do, but if I don't want to do any more reducing, I need to divide it by 10. Because if my numbers end in 0, I can divide by 10. And they both end in 0. So I get 1 over 3. So that's the first one. And then my second event. My second event says get a card that is not orange. So if I go up to what cards I got, there are 9 orange cards. So if there are 9 orange cards, how many cards does that mean that are not orange? Can't hear you, speak up. It's 21 because there's a total of 30 cards. And if 9 of them are orange, that means 30 minus 9 is the rest of them. So there's 21 cards. But I was getting there. No, you're fine. So, but just as Miss Williams was about to say, the thing is though, we already pulled out a card that wasn't orange. We put out a yellow card. So that means the number of total cards that are not orange went down. It went down to 20. So it's 20, but it's 20 out of what? It's not 20 out of 30 because we pulled one card out. It's 20 out of 29. There were 21 cards that were not orange. The first event was me pulling out a yellow card. A yellow card isn't orange, so that means I took one of the not orange cards away. So there were 21, now there's 20. Yep, I got 21 from just saying, adding all those up, there's 30 cards. If I take away the 9 orange, how many are left? 21. But if I take out one of the 9 orange, that means there's only 20. So that's where we got that. It doesn't look like we can do any reducing, so I got 1 over 3 times 20 over 29. I can't do any reducing there, so I just got to, 1 times 20 is 20, 3 times 29 is what, 87? And that's my answer. Nope, nope. This is divisible by 3, that's divisible by 2, 4, 5, 10. Like I said, the only thing I can think of is this is divisible by 3. So the last one, I want to get 2 cards that are neither green or red. So I go back to what we were talking about before, and I got 30 total cards. I want to get a card that's not red, so that means we're not including those 5, and not green. So if I take the green cards out and the red cards out, how many cards are left? 19. So that means my probability for my first event is going to be 19 out of 30. 19 out of 30. Well, if I choose one of those cards successfully, well, first off, you can't reduce this, but after that, so if that's successful, then I look at my second event, and I want to pull another card from that. Well, if it started with 19 of them, and I pull one away, that means how many are left? There's 18 left. But 18 out of what? 29, because I took one away initially. And 18 over 29 can be reduced. So I move on to the next part. I got 19 over 30 times 18 over 29. Now, while I couldn't reduce before, say it with me, butterfly. Okay, I guess don't say it with me, butterfly. So anyway, 19 and 29, there's nothing that they have in common except 1. But 18 and 30, they do have a number in common. They got several numbers in common, as a matter of fact, because 18 and 30 are both even numbers. So you could divide by 2. 1 plus 8 is 9. 3 plus 0 is 3. That means both of those numbers are divisible by 3. So you can divide by 3. But the divisibility rules for 6 say if you can divide it by 2 and 3, you can divide it by 6. So that's what I'm going to do. Divide the top by 6 and the bottom by 6. Right here I get 5. Right here I get 3. So I'm going to have 19 over 5 times 3 over 29. And so 3 times 19 is what, 57? And then 5 times 29 is what, that's 4. No, 5, sorry. Yeah, sorry about that. Okay, so yep, that's 5, carry the 4. 5 times 2 is 10 plus 4. So 145. And the top is divisible by 3. The bottom is divisible by 5. So nope, they're not. You can't reduce them, so there's my answer. So does anybody have any questions on dealing with dependent probability? Does anybody have any questions about dealing with dependent probability? Okie dokie. Okay, so we got a two-way chart now. Yay, two-way chart. So we got several questions that are coming from the information in this two-way chart. So you're gonna have questions, and the thing is to kind of feel out after reading the question what you need and what you're looking for. So, what is the probability that a randomly selected seventh grader likes tacos? So the thing that we're picking from is the seventh graders, right? So I need to look at the total number of seventh graders. So that's 50. There's 50 seventh graders. So what I want for my probability, I want the seventh graders that like tacos. And I'm going to put that over the total of seventh graders. So the seventh graders that like tacos, right there, 10. The total number of seventh graders is 50. Well, both of these numbers end in 0. So I can divide both of those by 10. And I get 1 over 5 as my probability. And that's that. Which lunch option is the most popular among all the grades combined? Pizza. Because when I look at the total of what food is whose favorite, I got 63 people that like pizza. So pizza is the one that's the highest. That's higher than all the other ones. All right, so next, what is the probability that a student who likes pizza is an eighth grader? So the stuff that we're picking out of now is the students who like pizza. So that's the total I got to look at. So I'm looking at the total of folks who like pizza because that's what I'm picking from. The probability of a student who likes pizza. So I got a total of 63. So what do I want? I want an eighth grader who likes pizza over the total people who like pizza. Okay, so eighth graders that like pizza. Pizza, eighth grade, that's 20 of them. And then the total amount of pizza folks is 63. And 20 over 63 cannot be reduced. So that's it. 20, it can be divided by 2, by 4, by 5, by 10. 63 can be divided by 3 and 9. Don't work, so you keep it moving. What is the probability that a randomly selected student likes salad? Now we're just talking about random students. Now we're just talking about random students. So because we're talking about random students, what's the total that I need to look at? 180. Excellent. I need to look at the total number of students. So total number of students is 180. And what am I looking for? I'm looking for the students that like salad. So the top is the salad lovers. And then the bottom, well, let's say students. The student salad lovers. And then the bottom is the total students. So that's going to be 30 over 180. 30 over 180. Well, 30 over 180 can be reduced. It ends in 0, so I can divide by 10. But it also, if I combine the numbers, 3 and 0, that could be divided by 3. 1, 8, and 0 is 9, it can be divided by 3. So I could also divide by 3. If you can divide by two different numbers and you want the biggest number that you can divide by, you multiply those numbers. 3 times 10 is 30. So 30 is what I'm going to divide by. Now you could divide by 3 and then divide by 10. You still get the same kind of thing, right? So if I divide by 30 top and bottom, I get 1 over 6 and I'm done. Now if you don't, just so we can be fair, let's start with dividing it by 10. So I divide by 10, I get 3 over 18. 3 over 18 is wrong if you stop there. That's not what you need to do. So the top and the bottom can be divided by 3, so I keep going. It's like I told you. If you stop, then it's wrong. If you keep going till you can't go anymore, it's fine. So I get the 1 over 6 if I do both of those. But what I told you about mathematicians, we only want to do division one time. We don't want to keep doing it. So we look for the greatest common factor, the biggest number that can be divided in there. The last one. What is the probability that students who like sandwiches is not a sixth grader? So what total number am I looking at now? The total sandwich lovers is what I'm looking at. Yep. Because if I look up her, and if I'm talking about the students who like sandwiches, these are all the students that like sandwiches. So that's 43. And so now what I want is um, sandwich lovers who are not in sixth grade over the total sandwich lovers. Okay, so the sandwich lovers that are not in sixth grade. Well, if I go back up here, sixth grade is 12. Nope, don't want that number. So I got 15 plus 10 plus 6. Just like my man said, that's 31. So I got 31 sandwich lovers that are not in sixth grade out of a total of 43. There's nothing that divides 31 and 43 except 1. So that's my answer. Does anybody have any questions? Does anybody have any questions? Okay. Say it again, ma'am. Yes, I'm explaining and I'm helping you to have maybe notes or something. So that's why I'm doing all of that extra. You don't have to write that. All you need to do is, I mean, you just got to write the answer. The thing is, though, the more work you show me, there's a possibility of getting partial credit. Say that you wrote this down right here. All right. Let's just say that. So say you wrote this down. You wrote sandwich lovers 43. You wrote the sandwich lovers 9th, 6th grade, and then you wrote 30 over 43. That's wrong. Now, if you showed me this and that, I might say, you know what? Maybe she just accidentally wrote the wrong number. She knew what she was doing. She knew exactly what she had to put there. She just put the wrong number by mistake. So, you know what? Maybe I can give her half credit. If the problem is only worth 1 point, I can say, oh, you know what? I give her half a point because she had the setup right. She just put in the actual answer wrong. Or say it was worth 5 points. And you know what? I'll give her 2.5. I might even give her 3 points because the setup was right. She just put in the wrong numbers. So that's why you always want to put down as much information as you can. Because if you just put an answer and your answer is wrong, I can't give you nothing. But if you put a setup, if you show me some work, I may be able to give you something. But what do you have to put? Just the answer. Unless the problem says something about show your work. And none of these do as far as I know. So draw a two-way table for the given information to answer the question. So in a group of 100 Boys and Girls Club kids, there are 45 boys who play basketball and 10 who did not. So they telling me how many kids I got in total. That goes right here. Not down here, not down there, not down there. That is my total. These two numbers are supposed to add up to give me my total, and these two numbers are supposed to add up to give me my total. So out of a group of 100, so that's how many I have total. There are 45 boys who play basketball. So play basketball and boys, 45. And then 10 girls who did not. So girls and did not play, 10. Okay, that's not enough information to continue my stuff. But if we go to this first question and read what it says, how many girls play basketball if there were a total of 50 boys in the group? That tells me some more information. So I need to use this question to finish my chart. So if there were a total of 50 boys, so there's my boys, there's 50 right there. That 50 makes it to where I can complete everything now. Because I know that the total, this number plus 50 is going to give me 100. So what's this number? Huh? That's 50. I know right here, this number plus 10 gives me 50. So what's that number? That's 40. I know that this number plus this number gives me my total right here. What's this total? That's 85. I know right here that 85 plus some number gives me 100. I also know that 45 plus some number gives me 50. So 45 plus 5 gives me 50. So that's 5. 10 plus 5 gives me this number, or 100 minus 85 gives me this number. Anyway, I look at it, it's 15. And so now I can definitely answer this question. How many girls play basketball? 40. I know. Huh? So, that being said, be careful what you wish for. I got another two-way table here with several questions, and then I've got another little chart that you can believe right here. So I'm gonna leave those to you. I'm gonna do the next one. So I'm going to leave that to you. So the next thing says circle the correct answer for each question. You roll a die. Die is just singular for dice. And then flip a coin. So I roll a die and then I flip a coin. Are those events independent or dependent? Independent, because the roll of the die does not affect the flip of the coin, so they're independent. You draw two cards from a deck without replacement. Without replacement. Are those events independent or dependent? They're dependent. They're dependent, right? Because without replacement means it changes the total. Standard deck of cards has 52 cards. If you pull one out, now you got 51. So it definitely is dependent. You pick a marble from a bag, record its color, and put it back before picking another. Are they independent or dependent? Independent, because you put it back. Because you put it back, excuse me, you don't change or you don't affect the second event. So that's independent. Um, you choose a student from a class to answer a question, then choose another student without putting the student's first name or the first student's name back in the hat. Well, probably should have said you choose a student's name out of a hat, and so whatever. But I think you get the gist without putting the student's name back in the hat. So are the events independent or dependent? They're dependent, because we didn't put the name back. So the total number of students that I got it went down. So now, if two events are independent, the outcome of one of the outcome of one event does not affect the outcome of the other. Is that true or false? False, true. What is it? Why you say true? Exactamundo. Independent does not rely on the other one. So, yep, the outcome of one does not affect the outcome of the other. So that's true. Um, Choosing two color balls from a bag with replacement is an example of dependent events. True or false? That's false. Because with replacement means I didn't change the overall value of the stuff. So then last but not least, we got Venn diagrams. This first stuff right here, that's just notes. That's just stuff. So over here though, the diagram below shows the game console students owned. How many students own a PS4? Everybody in this circle owns an Xbox. Now, if we said, sorry, a PS4. So if I said, how many students only own a PS4, then it'd have been 17 because those are the ones that only have a PS4. But see, the four they got both. So if I ask how many folks own a PS4, it's both of those. So that's 21. That's the 17 plus the four. And so conversely, how many? What? Yes, that's a question. How many students own a Xbox? 10. It's 6 plus 4. And then how many students own both systems? 4. Okay. Does anybody got any questions on that? Okay. Um, I might make another video on that on this second page, or I mean on this third page. I'll think about it. That way you can check it. So you got a set of problems that you can do